Today in this video I will be talking about second and other higher order derivatives. But before that, let me just remind you that this is the ninth video in the series of differentiation. If you have not seen other previous videos, please watch them. The links are given in the description box below. Alright, let's first quickly revise all the basic differentiation rules and standard derivatives, as these will be used frequently throughout calculus. So we have derivative of sum of functions, which is just the sum of individual derivatives. Similarly, the derivative of difference of two functions is just the difference of individual derivatives. Similarly, the derivative of product of two functions is given by the product rule, which is first function derivative of second plus second function derivative of first. When a function is in the rational form, we use quotient rule or division rule. And the rule is denominator into derivative of numerator minus numerator into derivative of denominator whole upon denominator square. Now let's have a look at some of the standard derivatives. Derivative of x raised to the power n is nx raised to the power n minus 1. This is also called power rule. Differentiation of e raised to the power x exponential function is same as e raised to the power x. Differential of a raised to the power x is a raised to the power x ln a. Derivative of ln x is 1 upon x. Derivative of trigonometric functions, sin x is cos x is minus sin x. Derivative of tan x is sec square x. Derivative of cot x is minus cos x square x. Similarly, derivative of sec x is sec x tan x, and derivative of cosec x is minus cosec x cot x. Let's say a function y equal to f of x is differentiable at a point x. Then its derivative f dash x is called the derivative of the first order or first derivative. So f dash x is equal to dy by dx is the first order derivative. So we can differentiate it again with respect to x, and it will be d by dx of f dash x is equal to d by dx of dy by dx. Now this d by dx of f dash x or f prime x can be written as f double prime x or f double dash x, which is also written as d2y upon dx squared. And this is called second order derivative. It can also be written as d2y or y double prime or y2. And similarly, this process can be extended for third order derivative or other higher order derivatives. Now let's see some examples of second order derivatives and other higher order derivatives. Let's say we have a question y is equal to x square plus 3x plus 2. When we differentiate it first time, it is dy by dx, and obviously the answer would be 2x plus 3. If I differentiate it one more time, I'm writing it in little detail right now. Dy dx is equal to upon d by dx of 2x plus 3. So if we differentiate, this side becomes d2y upon dx square is equal to straight 2, because the derivative of 2x plus 3 is 2. It is also possible to find out the third order derivative over here, which is d3y upon dx cube, and it will be 0 because it's a constant. Now once we have done this question on first derivative and second derivative, let's look at the animation which is prepared in Desmos graphing software. This red parabolic curve is our question function fx equal to x square plus 3x plus 2. This black line is the tangent line which is being drawn at the point c comma fc with the gradient as f dash c. Apart from this, there are 3 points. One, which is moving on the parabola, showing the current points on the curve. The black point shows the gradient at the current point, and the red point shows the second derivative value. The blue point, which shows a very important fact, that when the function is decreasing, its gradient is negative and lies below the x-axis, and when the curve is increasing, the gradient point lies above the x-axis. Also interesting to note here that the tangent line at the minimum point or the change point is parallel to x-axis, and the gradient of the function dy by dx is 0 over there. Also note the fact the second derivative for the question is 2. That is why the second derivative point is moving along the line y equal to 2. Another example, we have a function like y is equal to x cube plus tan x. So the first derivative will be 3x square plus sec square x. And if we find the second derivative, it is d2y upon dx square, which is 6x plus 2 times sec x times sec x tan x. So as a final answer, this can be simplified 6x plus 2 times sec square x tan x. Okay, let's take another example. We have a question like y is equal to 5 times cos x minus 3 times sin x, and the question is asking to prove that d2y upon dx square, which is the second derivative, plus y is equal to 0, which means we need to find out the second derivative. So let's first find out the first derivative, which is dy by dx is minus 5 sin x, and then we have minus 3 cos x. Now this is the first derivative. This can also be written as y prime, this can also be written as y1, this can also be written as d1. Now finding the second derivative, which will be d2y upon dx square, will definitely be minus 5 times cos x and plus 3 sin x, because the derivative of sin x would be minus cos x. Again, this can be written as y double prime, this can also be written as y2, or this also can be written as d2. So this is the different notations in which the questions can be asked in the exam. Now as per the question, we have to prove that d2y upon dx square plus y equal to 0. Sometimes question is very easy, because if you look at the right hand side right now, if I take the minus sign common, I am getting 5 of cos x minus 3 sin x. And if you remember, this was our original question y. So this was basically y. So I'm getting minus y on this side. So it is d2y upon dx square is equal to minus y. Finally, it can be written as d2y upon dx square plus y is equal to 0. So sometimes questions are easy like that. We just take the second derivative, and if we just manipulate the right hand side, we can get the answer this way. But sometimes when the question becomes little complex on the right hand side, then it is also a good approach to find out all the individual elements one by one, maybe dy by dx if it is required in the question, or d2y by dx square if it is required in the question. Find out all the elements and just substitute them in the given expression as the question, and you will get the required right hand side. So let's take a question which is y is equal to 3 times e raised to the power 2x plus 2 times e raised to the power 3x. This is the given y, given function, and we are supposed to prove that d2y upon dx square minus 5 times dy by dx and then plus 6y is equal to 0. Though still you find the second derivative and you manipulate the right hand side to get this expression, but it is a good idea to solve for first derivative and second derivative and substitute all the values back in this given equation to get the final answer. So this is the final thing that we have to prove. So let's start with the first derivative first. So obviously dy by dx would be 3 times e raised to the power 2x into 2 plus 2 times e raised to the power 3x into 3, which means can be written as 6 times e raised to the power 2x plus again 6 times e raised to the power 3x. Now that's the first derivative. So if we go ahead and find the second derivative, it should be d2y upon dx square is equal to 6 times e raised to the power 2x into 2 because of the chain rule, plus again 6 times e raised to the power 3x into 3 again because of the chain rule. So if we simplify this value becomes 12 e raised to the power 2x plus 18 e raised to the power 3x. So I have the first derivative ready now, I have second derivative ready now, and I have the original y ready now. So if we go back and substitute all these values in the given equation, we can get the right hand side as 0. So let's say the given equation was d2y upon dx square minus 5 times dy by dx and plus 6y. If we substitute all these things in this one, then the right side must come out as 0. So going ahead, d2y, let's put the second derivative first, which is 12 times e raised to the power 2x plus 18 times e raised to the power 3x minus 5 times, let's substitute the value of dy by dx, which is 6 times e raised to the power 2x plus again 6 times e raised to the power 3x, and then plus 6 times y. The y value is 3 times e raised to the power 2x plus 2 times e raised to the power 3x. This is still the left hand side going on. Let's simplify. Do we get 0? 12 times e raised to the power 2x plus 18 times e raised to the power 3x minus 30 times e raised to the power 2x. Similarly, minus 30 times e raised to the power 3x and plus 18 times e raised to the power 2x plus also 12 times e raised to the power 3x. So here now we can see this is 12 e raised to the power 2x and this is 18 e raised to the power 2x. Together it is 30 e raised to the power 2x, which can be cancelled with minus 30 e raised to the power 2x. Similarly, we have 18e3x is here and we have 12e raised to the power 3x is here, which is together positive 30e raised to the power 3x, and we have minus 30e raised to the power 3x here, which will cancel each other. So ultimate we are getting the right hand side as 0. Let's see one more question. If y is given as cos inverse x, y is given as cos inverse x, then we have to find out the second derivative d2y upon dx square in terms of y only. So this means little bit of manipulation would be required in terms of y only. So in this case, let's start with y equal to cos inverse x. So obviously it can be written as x is equal to cos y. If I differentiate, it is a function of y, x is equal to cos y. So I can differentiate this both the sides. So it will be dx by dy is equal to derivative of cos y will be minus sin y. And since I am differentiating with respect to y, so it should be 1. Derivative of y will be 1. So from here, we are getting dy by dx is equal to minus 1 upon sin y, which can also be written as minus cosec y. So if I have to differentiate it one more time, because I have to find the second derivative, so d by dx of dy by dx will means minus d by dx of cosec y as well. And one interesting thing is I am differentiating with respect to x, though the function is of y. So obviously on this side it will be d2y upon dx square, while on this side derivative of cosec y will be minus cosec y cot y minus cosec y cot y times dy by dx, because it is a function of y and we are differentiating with respect to x. So overall answer would be cosec y into cot y into the value of dy by dx, which can be taken from here, which is the value of dy by dx can be taken from here. In fact, it is minus cosec y. So this value we can pick from here as minus cosec y. So overall answer is minus cosec square y times cot y. So we can see the second derivative now is written entirely in terms of y. Well, if you could understand what I was trying to explain, please like and subscribe to my channel. And if you want to be notified for my next video, please press the bell icon also. Thank you.